So another problem with this open-ended generation when it comes to the maximum likelihood decoding. So maximum likelihood decoding both involves, I'm talking about the greedy and beam both. So I'm talking about the greedy and beam search both. They are maximum probability based decoding, because in greedy we are selecting the maximum probable word at each step when we are generating a next word, and in beam also for all the candidates we are at the candidate level, at least we are selecting the candidates based on the maximum probability. So what is the problem with that? When we deployed such a system, and let's say this is from a real deployed model, it was asked that given this context, it needs to generate a story, and it started pretty well. You can see in the black text here that it generated coherent story till this point. But when it generated this name of a university, Universidad Nacional Autónoma de Mexico, it started repeating the same thing again and again. So this problem, people have found out that when you apply this maximum likelihood decoding kind of scheme, then it can do repetition a lot. So model is kind of tending towards doing lots of repetition when it generates the text. So it seems like for the, so we had this spectrum, which you might remember, that we had the low entropy kind of task and the high entropy kind of task. So empty and summarization were here, and story generation was lying here. So it turns out that these maximum likelihood decoding or maximum probability decoding kind of methods, both greedy and beam search, they kind of bias towards this low entropy task, and they are super good at doing machine translation or maybe somewhat summarization. But when you apply these decoding scheme to story generation kind of task, then it suffers with many problems like hallucination and also repetition. So what could be the reason for this repetition? That there is a phenomena called self-amplification. So here is the normal, a kind of a trend which the normal decoding with the maximum likelihood or maximum probability based decoding scheme, let's say greedy or beam search. So here we can find the normal pattern. So when you see here, and it generated, let's say, the text I don't know. So it generated I don't know with this normal pattern, and in the y-axis you can see negative log likelihood. So the how whether it should be probable to generate this word or not. So you can see it goes to the score 5 or so. But once it generates this, once it generates once I don't know, and then let's say it's again generated I don't know, it starts to generate I don't know repetitively, and in terms of negative likelihood, you can see the negative likelihood is going down. That means the probability is going up. So probability of generating this I don't know is getting up and up by once it generates the I don't know multiple times. So model is becoming more and more confidence to generate I don't know, and it says that this is what the correct thing to generate. So what we have seen, that if model generates something multiple times, let's say I am tired, and it has kind of tendency to generate the same phrase again and again, and the probability of getting I am tired being generated, it becoming more and more. So negative likelihood is going down, that means probability is going up. And other problem is, or maybe other observation is, people tried out small LLMs and large LLMs. So they found that the both of these kind of models, having large parameters or having very less parameters, they both struggle with it. So scale of the model doesn't solve it. So that's what they found. So what can solve it? So we need to change, or we need to deal with the decoding scheme itself. So that's where the root cause is. So then what could be the way out or possible solutions for this repetition problem? So they found out very intuitively that what you can do, you can find the n-grams. Let's say in the previous example, you can see the n-grams of I am tired, and then you find that this n-gram is appearing again and again. So what you can do is, you can condition on the generation that model should not generate the same n-grams multiple times. But obvious kind of an obvious problem with this issue with this is that in some cases we might want to generate repetitive text. Let's say a place name, or name of some entity, or name of the protagonist in the story, and so on. So in that case, this will fail, and it will won't generate the appropriate text. More there are some more complex alternative for that, and which could be unlikelihood objective. So rather than having negative likelihood, we should have unlikelihood objective. So we change the objective function, and where we penalize the generation of similar things which already maybe model has generated before. And other thing is coverage loss, where the attention mechanism itself might want attention mechanism itself won't attend to, or more will not give focus to some of the words which are already generated. So it will give attention to the things which are not generated, or which are not common. And so it will attend more rare words rather than more common words. So that's the core idea behind this technique. And then there is a contrastive loss which is super interesting, where they utilize a small let's say model having less parameters, and having a large model having more parameters. So what they want to do, so if you want to generate a text, so you give input to both of these LLMs, and they generate the text, or maybe at the word level, maybe the probability distribution itself. So let's say it generated the probability distribution, it generated the probability distribution for the next word. So what you can do, you can take the subtraction, take the difference between these two, and the things which might be similar or giving more importance to repetitive word will be here also, and they will be here also. And so what this technique will do, when we will take the difference, those things will kind of cancel out, and then what is left will be more rare words, or maybe newer or novel words will be left, and the things which were kind of repetitive will be cancelled out. So this is very interesting technique, and it needs further research how effective this is for in case of, let's say, open-ended generation versus more constrained generation having low entropy. So another thing what they noticed, that this maximum likely string generation, or maximum probability based decoding, the problem is, the objective of NLG, what we have talked about when we were starting the topic, that one of the objectives is to generate the text which is similar to human generated text. And in this graph, what you can see, this peach colored graph is the is the distribution of probability of text generated by humans, and this blue curve is for, let's say, LLM. So what they found out, when you apply this greedy decoding or beam search kind of decoding scheme having max probability based decoding, then they found out that the kind of distribution trend of the word selection by humans is very different than the word selection by LLMs. So LLMs is kind of more less, or it's less fluctuating, but in case of humans, it's like lots of fluctuations are there. So human might go from one end towards other end very frequently. So they might be selecting very rare words and all out of the blue, and then the model, what LLM is doing, selecting all the most probable word which are not maybe very rare when depending on the context. So when we can say that the uncertainty in case of humans are super high, but in case of LLMs, when you apply a beam search kind of decoding, the uncertainty is not high. And when you don't have uncertainty, it's not, you won't be able to generate things which are interesting. So the story will be generated, but it will be very repetitive in a sense that when you generate 100 stories, most of them will be having some common kind of plot. So we won't be able to be creative in that sense. So again, super good techniques people have already proposed to do away with those issues which we have discussed so far. So one of the techniques called random sampling, and super intuitive and very simple. So what you want to do, given, let's say, this example, that he wanted to go to the, and the next word model needs to generate. So what you will do in the max probability greedy decoding or beam search, you might say that restroom, because it is, and this is the probability distribution for this over, let's say, your vocab. This is the probability distribution. So with the max probability decoding kind of scheme, we'll select either restroom or at most grocery, and most of the time like restroom itself. But what we want more creativeness, or more novelty in text. So how about generating hospital or maybe gym and so on, which are less probable, but they might be more interesting for open-ended generation. Okay, so in case of kind of a decoding schemes, vanilla sampling, if you do vanilla sampling, then it's very heavy tailed. You might have seen that I haven't shown lots of other words, so your dictionary won't be just 10 words, it will be having, let's say, 10,000 other words. So you will be having a probability distribution over your vocab, and then this tail is very long. So how do you sample? So one of the solution for this heavy tail, we cannot kind of incorporate for all the possible candidate words. So what we can do this top case sampling. So rather than selecting from and to solve the problem of sampling, how to select randomly, so they say that we can go for the top case sampling, and when we do this top case sampling, and this value of k can be adjusted or tuned for your task or for your model. So let's say he wanted to go to the, and it goes to the model, and then you got the probability distribution, and the value of k, let's say in this case, is 4. So you select these 4 words, and you won't consider these words. So what are the pros and cons for this k sampling, top k sampling? That if you increase this value of the k, let's say you have, rather than 4, you have 8, then, or more maybe, then you will kind of consider pub, or maybe you wanted to go to the doctor, maybe here it comes somewhere here, and the value of the k is large, let's say it's 70 or so, and at 69th position or 68th position, you will get something like moon, or maybe sun. So he wanted to go to the sun, which doesn't make much sense, because and it's pretty obvious why. So in case we increase the size or increase the number k, then what we will have more diversity. Maybe we'll be making generating more diverse kind of text rather than generating just the restroom, grocery store, airport. We can generate pub, gym, hospital, and so on. But it is too risky, because it can also generate something like sun, or maybe it can generate to fire or volcano and so on. And if in case we decrease the k, so we decreased it to, let's say, this 2 or 3 only. So it is safe option. So you won't generate something which is out of the context, or maybe not super logical, but it will generate things which are generic. So it will be again boring. So in a sense, if we discuss the problems, let's say this problem and example I've taken from a PhD student from Stanford. She said, and I never, and then need to fill it. What would be the next word? And if top k sampling can cut off too quickly, so we cut it off here because of the k. Let the k size is only here, but there are some of the words here. So it says that I never wanted, I never told, I never liked, I never had, and I knew. But it didn't say, let's say, I never watched, or I never saw. Saw is there. Maybe I never went to, or maybe something which is more interesting. So we are cutting off the probability distribution too early. Maybe some of the interesting things we are missing out on. On the other hand, top k sampling can also cut off too slowly. In some of the cases, let's say it says I ate the pizza while it was still, and then the most probable thing is hot, because you want to eat pizza when it's hot or warm, or when it was cooling, maybe less probable, or when it was still heating. That doesn't make much sense. But how about the cold? So we can in sample these things are also appearing, but they don't make much sense. So nobody wants to eat pizza when it's cold, or maybe when it's burning, and so on. So we can see the clear problem. What are the problem associated with top k sampling? And very simplistic solution or hack to this problem issue is top p or nucleus sampling. And the core idea, like, rather than going into complex things, is rather than going for top k occurrences of the words or the probabilities, we can see where is the density of the probability, where the density lies of the probability. So your k won't be fixed here. Your k can vary because of the density, the distribution of the probability. So that's what the core idea is. So when the probability distribution is flatter, we can have many options. We can stretch the k, and when the probability distribution is peakier or more skewed, you can reduce the size of the k. So that's the flexibility is given by this top p or nucleus sampling. So if we see with an example, so what happens is, this is the top k sampling. So let's say we are having this probability distribution, we have this probability distribution, and so on, this probability distribution. Then we apply the probability p sampling based method. So in case of this, we can see it's kind of a more in between. So your size could be in between. The k size is kind of average a k size or mediocre. And when your distribution is more flatter, so that means the probability is distributed more, so your k is kind of more here. Your selection range is more here. And when it's very skewed, you can select from top itself and you'll get the right answer. So it's kind of the range got reduced a lot. So you will be selecting from this part of the distribution itself, where in this case you can go further and select from more viable options, maybe lying lying down the line, and here it could be in between, where we can select halfway down in the distribution itself. So there are other methods which we will not discuss in this lecture. It's typical sampling, where they kind of propose that, so rather than just probability distribution, you can also kind of condition it with the entropy of the distribution, where the more entropy will suggest you to go for having more range, increasing the range, or having less entropy, you can decrease the range. So it will be kind of a dynamic selection of the probable or viable words based on the value of the entropy that you calculate. And other kind of suggestion or improvement on top of nucleus sampling is there should be a lower bounding valid probability. So what he means by that, so let's say this is more flatter, and then you need to increase the probability. So there might be some words which are there in the range because of this probability distribution, and but they are not super contextual in terms of like adequate context, or maybe they are not they don't make much sense to add to that sentence. So if that is the case, then they propose that for each of these distribution, if the probability goes beyond a threshold, and let's say that is p1, a threshold. So if the probability goes beyond the threshold for some word wt, then you don't have to select it. So you need to cut it from somewhere. Even if the nucleus sampling says that the range should be this, but you have this threshold, so you need to cut it from here. So that's what they propose, and in their experiments it works well. That's what they showed. So another important thing which is left is temperature tau. People who have already seen generation, so people they use in softmax expression itself, they divide the scores what you get, or maybe logits divide by the temperature tau, and it has kind of very orthogonal effects when you compare to the random sampling or nucleus sampling and those decoding schemes. So what do I mean by that? When you divide this with this tau, and you compute you get the probability distribution. So maybe this is the probability distribution originally, this might be probability distribution again, maybe it got big, maybe got reduced, but the pattern will not be different. So let's say A comes after B, and in this distribution, then A will again come after B with similar kind of pattern. So their relative position will be the same, but their trend will be the same, but kind of difference might change a bit. So what do we get from tau? So how can we kind of tune the distribution using the temperature variable tau? So if we rise the temperature tau greater than 1, then your distribution will become more uniform. So let's say it was like this, and then if you apply the tau, it can become like more flatter. So this you should do for if you are using or generating, you are applying NLG for open-ended tasks, so or story generation, or having high entropy. On the other hand, if you lower the T, then the distribution will become more spiky. So let's say this was the distribution originally, so you apply the tau, you can go back to this. So you decrease the tau or lower the tau, you can go back to this. And why you want to do that? You want to do this for in case of low entropy kind of tasks, which are maybe summarization or empty and so on. So with this tau, you have kind of a tool to tune your decoding to kind of cater to different tasks, let's say having low entropy and high entropy task. So there are some further improvement which we can skim through. So we are decoding bunch of candidates, right? In beam search or maybe some of the other samples from the sampling also. We are decoding bunch of the candidates, and then what we can do is we can re-rank these candidates. And prune them. We can re-rank them based on some sort of attribute. So one of the attribute is a perplexity, which we are familiar with, and the problem with this is repetitive utterances generally get low perplexity. So what we want at the end in the generation, that perplexity should be low, and when there are many repetitions, then when there are very many repetitions of the same thing, then the perplexity for the repetition will be very low. Then model will want to generate more repetitive utterances or maybe repetitive phrases. So another thing what we can try out, we can rank the candidates based on some sort of attributes, which could be style, could be discourse, could be factuality, how factual the current generation is, or logical consistency, and many more. And you need to calibrate these pretty well. So you need to see, given the model, you need to fine tune it and calibrate it so that you get the better result by re-ranking. And you can also combine multiple re-ranks. So you can, let's say you do entailment of already generated candidates hypothesis, and then also you condition on up style. So based on the style plus the factuality or entailment, you can combine these two kind of attributes, and then you re-rank them, the candidate which are generated.